And obviously, at the surface, once the species start to diffuse, the profile, if we were to look at the concentration versus the depth into this bar, changes with time. Okay, FCC iron carbon alloy, initially containing 0.28% carbon, is carburized at high temperature and atmosphere, where surface carbon concentration is maintained at 1 weight percent. After 49.5 hours, the concentration of carbon is 0.35 weight percent at 4 millimeters below the surface. The question is to find the temperature at which this treatment was carried out. Okay, and this is the non-steady state diffusion, where this is the equation that describes this diffusion process. C of x and t. You can see here that the concentration gradient changes as a function of position x and time t. And C0 is concentration somewhere in the bulk far away, and CS is the concentration on the surface, right here. And then it's described by some sort of a mathematical function. The solution is this arrow function of x divided by the square root of dt, where d is the diffusion coefficient and t is the time. So here is and x is the position. So here is the link between the position and the time, and the arrow function is something that is tabulated. So I always keep saying that students in material science, their math skills, there are no material science majors here, right? We don't have we have a materials certificate, but not a major. The math skills of students in mechanical engineering is superior to ones for materials, because in mechanical engineering you actually have to solve a differential equation of the beam bending. And then there are Microsoft engineers. You know the difference? 3 engineers are driving a car. Electrical engineer and a chemical engineer and a Microsoft engineer. And the car stops. And they don't know what to do. So the chemi guy says, okay, let's make sure that the gas is actually transported to the engine through the carburetor. So they open it up and they see that the gas is flowing. Electrical engineer says, let's check the spark. So they open one of the spark plugs and they try to run the machine, and they see the spark. And you know what the Microsoft engineer said? What did the Microsoft engineer say? He said, I know what to do. Let's close all the windows, get out of the car, get back in, open all the windows, and maybe it will work. Okay. We use this equation to solve the problem. And the time is 49.5 hours, and the surface concentration, 0.35 weight percent. C0 is 0.2% at a distance of, 4 millimeters? So 4 times 10 to the minus 3 meters. And CS is 1 weight percent. So we plug everything into this equation to find the value of the arrow function, which is 0.8125. I mean, this is simple stuff that we can just calculate what it is. And then, looking at the table, we see that there's a value of the arrow function for 0.9 and 0.95 that are equal 0.7970 and 0.8209. And what we've calculated is somewhere in between. See here? It's not in the table. And what we're going to do is we're going to do linear extrapolation for the arrow function. So for the z, the arrow function value is 0.8125. And we can write that z minus 0.9 divided by 0.95 minus 0.9 is equal to 0.8125 minus 0.797 over 0.8209 minus 0.7970. And from this, we can solve for z to get 0.93. And you can see that it should be somewhere in between 0.9 and 0.95, and we calculated 0.93. So it makes physical sense, right? And then if we solve for d, for the diffusion coefficient, that's what we need, because the diffusion coefficient would allow us to calculate the temperature. So d is equal to x squared divided by 4z squared t. And in fact, you're going to see this quite a bit for most of the problems, that this diffusion business is proportional to the square of the distance and inversely proportional to time. And we can calculate the diffusion coefficient based on 1 hour, which is 3,600 seconds. So the key here in all of these problems is to make a proper conversion into the SI units. You know, meters, hours into seconds. And once we know the diffusion coefficient, we can solve for the T, which is equal to the activation energy divided by R, log of D0 minus log of D. And to find out D0, there's a table in the book that gives you the diffusion of carbon and FCC iron. So D0 is 2.3 10 to the negative 5 meters squared per second with the activation energy of 148,000 joules per mole. And that allows us to calculate the temperature, which is 1300 degrees Kelvin. And then you need to pay attention of how what is being asked. It says, determine the temperature at which the treatment was carried out. It doesn't specify, right? So both answers are correct, but if mastering is specifying that you need to give your answer in degrees C, you need to convert 1300 degrees Kelvin into degrees centigrade, and that's going to give you 1027 degrees centigrade. So at 1000 degrees, for 2 days, the diffusion length is 4 millimeters for that carburization of the gear. And if you go back here and look, you know, there's no length scale that you can see. You don't know how big is this gear, right? But 4 millimeters is something that you can see with your naked eye. What is the motto of this class? To control the process, to control the structure, to control the properties. Okay, what is the process here? Carburization. Keeping this part at 1000 degrees centigrade for 2 days. What did that do? It produced a hard skin layer, which probably improved the performance of the gear so that it can survive a lifetime. And then if you're an industrial engineer, then you would calculate how much it would cost. This may be a bottleneck of your process. You know, 2 days is a long time. Yes? And what do we have here? Civil, mechanical, and industrial? Right? Any questions about diffusion? It's amazing that one guy figured this out. So there's first fixed law and the second fixed law. One is steady state, one is non-steady state. Okay. There are two types of diffusion mechanisms. One is vacancy diffusion, the other one is interstitial diffusion. Which one is going to be faster? And why? What's a vacancy diffusion? You need to have an empty spot right next to you so that you can move there. But if you were a squirrel, you don't need an empty spot. You can just jump between the positions here. Which one is going to be faster? Interstitial diffusion is always going to be faster, because it does not require presence of the vacancy, and the concentration of the vacancies is controlled by what controls the concentration of the vacancy? Temperature. It has exponential dependence on the temperature. What you're going to see in this class is everything has exponential dependence on the temperature. So that natural log business that I showed you, practice it, because that's how most of the problems are going to be. Now, right after this class, I teach another class which is called Mechanics of Solids. And what we're going to do now is we're going to have Mechanics of Solids course in one lecture, or 2 lectures. And I'm going to try to explain to you, to the best of my ability, of what the heck this means. I carry all of my handouts with me. So I have this rubber band. You can see, I'm stretching it and it goes back. What kind of deformation is this? Can you see it deforming? Huh? It is expanding, so that's under tension. And under tension, is this becoming longer or shorter? Is that a plus or minus? It's a plus. So which kind of deformation, and as a result the stress, is considered to be positive? There are 2 types, tension and compression. This is what? This is tension. And tension is positive. Yes? Okay, you're going to remember this. You're going to remember this rubber band for the rest of your life. You're going to remember me for the rest of your life with this rubber band. And I explained to you that plus is a plus and a minus is a minus. It's very common for humans to get it backwards, the plus and the minus. And I don't know why, but I think philosophically this is the reason why AI makes the same mistakes and humans do mistakes that philosophically are the same. They can take a body of a human and rotate it 180 degrees, which does not exist in nature, but it does it for, 6 fingers in one hand and 4 on the other. Overall it's 10, so, elastic versus plastic deformation. Plastic deformation is my paper clip, which I don't have, but I'm going to use this piece of paper. So what I'm going to do is I'm going to bend this piece of paper 90 degrees, and you can see I just bend it 90 degrees, right? See it? Okay, and I'll let go. What happened? Did it go back to its initial position?
No.
No, it did not. Okay, and you can imagine me doing this same thing with a paper clip, right? Okay, so we're going to talk about this from the perspective of the materials and what is happening during plastic deformation of a metal is we are generating and moving dislocations. And what's a dislocation? Interruption in a pattern. Okay, what kind of interruption in a pattern? Extra half a plane, and to induce a dislocation, what kind of stress do we need to apply? Strain, stress, what kind? There's normal and then there's shear. Shear. So we introduce shear stress, right? And we introduce that half a plane, or if it's an edge dislocation or screw dislocation, doesn't matter. The idea is the same. And eventually this dislocation is going to travel and emerge at the surface, right? Which gives us persistent slip bands. Okay. So during plastic deformation, atoms, planes of atoms, physically move, correct? And then after they have been moved, what happens once we let go? They don't come back. They only go there, very good, they only go there and they stay there. They don't come back. But the atoms are still stretched, right? Because it's under load. You know, like I'm keeping the load at 90 degrees, you can see. And this paper is actually pushing on my finger. Okay? But once I let go, what is the nature of this springing back? What kind? Plastic was during loading. Yes, unloading is elastic because plastic deformation happens by the motion of those planes of atoms. And those planes of atoms, once they move, they stay there. But there's still some springing back. What I'm trying to say is that no matter what kind of deformation you have, unloading is always elastic. Unloading is always elastic. Write it down. Unloading is always elastic. If I have elastic deformation, the unloading is elastic. If I have elastic and plastic deformation, unloading is always elastic. Now, once we have this discussion, let's dive in. Because we're going to talk about stiffness, strength, ductility, hardness. To control the process, to control the structure, to control the properties. So this is all about properties. Okay, common states of stress. There's a certain force. You can see this mechanism. It's in operation. This is a ski lift, right? And in the cable, here's a cable. We take this portion of the cable, and we draw a free body diagram for this cable, and you can see it's under tensile force. We're pulling, pulling on that cable. A0 is the cross-sectional area of the cable without any load, and the normal tensile stress is equal to the load divided by the area. When you see the letter sigma, it automatically implies that the stress is normal. So please write down sigma is normal stress. And it's equal to the force divided by the area that is perpendicular to that force. And what is a force? Mathematically, okay. Is it a scalar? Is it a vector? Is it a tensor? What is the force? It's a vector. And vector has two attributes mathematically. It has the beginning point, and it has the final point, and a direction. Right? That's a vector. Straight line, beginning, end point, and a direction. Like very opposite to this. Yes? Do you know the difference between vector graphics and raster graphics? Because they don't teach you this stuff explicitly. When you have a cell phone, do you have a cell phone? Okay. Who has an Android? What's the resolution of your camera? Anybody know their resolution? I'm not asking iPhone people because iPhone doesn't really tell you, or you don't care if you have an iPhone, what's the resolution. How's the resolution of a camera measured? Megapixels. And what is a megapixel? A mega is what? A million. Okay? So a megapixel is the matrix of those pixels. Correct? But it is square. So if you have a square, what would be the size of each side if you have million pixels? Mathematically. Square root of a million, which is what? What's the square root of a million? Is that right? He's right. So take your calculator and multiply 1,000 by 1,000. What do you get? A million. Yes? So 1 megapixel means that you have 1,000 pixels horizontally and you have 1,000 pixels vertically. Does that make any sense? Okay. And how many megapixels is your cell phone now? Anybody have any idea? Take your cell phone. Take your cell phone. Take your cell phone. Go to your gallery of the photographs. And pick up the recent photograph and blow it up. Like zoom in. What do you see? How can you tell? It's very small, zoomed in by pixelation. You see pixels. Do you? You don't? You cannot zoom in anymore. Maybe it doesn't let you. The software doesn't let you zoom in. You know what I'm talking about. You all know what I'm talking about. Okay. Here. It's not going to zoom anymore. So the maximum is, I don't know, 500. Loss in quality here. How about here? Yeah. This is the difference between raster graphics and vector graphics. For the vector graphics, this is vector. All of this is defined as a combination of mathematical points with the coordinates. And you can just scale it up. So when you have drawings, CAD drawings, they're all done in vector graphics. If you anytime you have a chance to use vector graphics, use vector graphics. Because raster is that. And I want to go back. So force is a vector. What about the area? Leave that thought for a moment. Now, here you see, this is a shaft. And the shaft is under torsion. Today we're going to talk about torsion in mechanics of solids class. There's a bending moment and there's a torque. And then this shaft is under a different type of loading, which is called torsion. And the shear stress, tau, is equal to the F divided by A sub S. And F is the force. It's also equal to m divided by ACR. R is the radius of the shaft, circular shaft, and m is the moment. Anytime you see tau, it automatically means that it's shear. And what is not emphasized here is that shear force is in the plane. It's like this. Normal force is perpendicular to the area, to the plane. Shear force is in the plane. Compression is another type of loading. Here's, if anybody has been in Arizona, or maybe it's not Arizona, but in Arizona they have things like that. Compression is opposite of tension. Also, normal stress, sigma is equal to F divided by A0. This portion of the bridge is also under compression. If you want to determine if the structure is under tension or compression, assume that it's made out of rubber and let it deform. And you're going to see which way it's going to deform. The rubber here, I cannot really put in compression, can I? I do put it in compression, but it buckles. So, other types of stress. Biaxial tension. Biaxial tension is the surface of the cylinder, which is pressurized from the inside, has two stresses that are in the plane. And this is a, yes, sir?
Sorry, isn't that different? Isn't that just a piece of the component that you take out and then it's just that they use that area and then you reference it to the rest of the tank and you use loop
Well, I can tell you that when this thing fails, it fails as a whole thing. It doesn't fail as a little tiny piece. But you're right, we're looking at a very small element, which is part of that. Now, civil you guys have to take mechanics of materials, it's called. Industrial, you don't have to take the course. And this is covered in chapter 9, which is combined loading. So question to you. Is there out of plane stress component? So you're right, there's a hoop and is there a stress component that's perpendicular? And by equilibrium, yes, so there has to be. Okay. Out of plane stress, I would call it, to be exact. But if it's out of plane stress, what is it going to be equal to? If it is an internally pressurized cylinder. It's going to be equal to the pressure inside. And the reason we ignore it is because those two stresses are at least 10 times higher. So we just ignore that one. Now there's hydrostatic compression. What does that mean? Are you guys under pressure?
All the time.
You're not? What is that called? Under pressure atmospheric. It's called. Yes? Now how much is that atmospheric pressure? 1 atmosphere, right. Yeah, it's very simple. But any of you ever dived? Okay. How deep can you dive without any specialized equipment? Have you ever swam in the ocean? Okay. Did you go under the surface of the water? Never, ever? You hate it because you cannot breathe. You get salt in your eyes, or you can wear goggles. You don't like it. But what about fresh water? Is okay? All right, so let's get environmental stuff out of the way. How deep can you dive? But what happens when you dive? Pressure where? In your ears. Your eardrum feels the pressure because that's a membrane. And that membrane feels the pressure, it moves. And when it moves, it hurts. And people train to dive to certain depth, right? Bottom line is that just like all of this atmosphere is pushing on you, if you go underwater, water pushes on the fish. And it's considered to be hydrostatic compression because this water pushes everywhere around. So this little fish. In fact, there is some fish that for deep sea fishing, if you take it out, the fish expands. I heard it's true. I've never seen it myself. If you have, any of you fish, you've seen it? You take a picture?
Is it 50 meters?
50 meters.
Yeah.
And what? The eyes pop out of the sockets?
Yeah.
You've seen it? You've seen it? Okay. Testing. How do we test all this stuff? There's a frame, and here's a sample. And there is a ASTM standard for this kind of test. Standard. And there's a load cell, and I brought that load cell to this class, did I? And maybe it was another class. Did I actually bring the load cell here? I did not? Okay. Tuesday, if I don't forget, I'll bring it. There's a device called the load cell that gives you the reading of the load. And there's another device that measures the displacement. So when we do the stencil test, we measure by how much this thing elongated, and we measure how much force. So you can imagine I can take some weights, right? And I can put those weights here, and as a result of me putting weights on the sample, it's going to sag down. And if I put more weights, it's going to sag down more. I'm going to put more weights, it's going to sag down more. And I keep loading it up to the point where it's going to fail and fracture. Okay. Typically, that's how it looks like. Moving crosshead, if you ever get into the materials testing business, you're going to have a job for your life, because anybody who's in the commodities materials, when you sell, you need to provide the spec to the customer, and the customer is not going to, most of the time, accept what you told them. They would want to test it themselves. So you can be working for materials testing on the supplier side and on the customer side. You see what I mean? And it's a multi-billion-dollar business. In fact, look it up. I want to know, what is the size of materials testing business? How many billions of dollars is that? Okay, so there's a machine that can do a tensile test. And another important thing is there is Poisson's effect. And the Poisson's effect, if you look at this rubber piece, and I'm stretching it, what happens to the lateral dimensions of this rubber? It gets thinner, right? Less wide. Okay? That's called the Poisson's effect. So for tensile stress, this is the force, this is the area. Area is perpendicular to the force. This is the normal stress. We use A0, even though the cross-sectional area is changing as we're applying the load. But we're taking original load. And when we do that, it is called engineering stress and strain. If we were to take and measure by how much it shrinks, we could get instantaneous stress and strain, and they're called true stress and strain. So true versus engineering. For the shear, tau is equal to the F over A0. The units of the stress are pascals, because they're the units of pressure, force over area. And Megapascal is 10 to the 6 pascals. Sometimes it's expressed in pounds per square inch in English units. And that's where the confusion could possibly come from. I personally prefer SI units because I was trained in the SI units. You go to Canada, everything is in kilometers and kilograms. You cross the border. Ever been to Detroit? Anybody? Have you ever been to Detroit? What about Niagara Falls? Anybody has been to Niagara Falls? No? There are certain areas between the United States and Canada where you can cross the border, and then you can see the difference between the English units and the metric units. A lot of Canadians come to Florida to vacation and they bring their cars. And they can't really sell their cars in the United States. Do you know why? Huh? What's on the driver's seat? Right hand side in Canada, in Hong Kong, and Thailand, and Japan. Anybody been to Japan? It's okay. You get a job, make some money, and then you can travel. Or better yet, your job sends you to travel, then it's travel is free. Yes, sir.
You're from China, you said, right?
Yes.
Hong Kong too?
Yes.
Because I know that I think in China they drive like here, the steering wheel on the left side.
Yes.
And in Hong Kong is the other way because it used to be part of England. So how do they do it if you go by car from Hong Kong to China?
You don't.
You can?
You can, but you're going to be screwed up. I can tell you that everything is on the opposite side, right? So when you try to make a turn, right? The blinker, which side is it on? You don't even know. Once you turn, where is it? Is it on the right or on the left? So you have two things sticking next to the steering wheel. One controls the wipers, and the other one controls the blinker. And on the car that's driven where the steering wheel is on the right side and you're driving on the left side, they're reversed. So you flip it saying you're going to turn to the right and to the left, and your wipers go on. So it's a mind. Nah, you know.
I think the hardest problem is that I don't drive a manual car, but if I did, I have to
Yeah, with the left hand. You have to. The stick would be on the left. Yes. How did we get on this subject? Man. In Thailand, it's very common to get a motorbike, a scooter, and then that's where it can be very dangerous. Because when you're in the car, you're protected from the environment if there's an accident. Brings up my memories. Okay, engineering strain versus true strain. And so the tensile strain. Now what is strain? Strain is deformation. And this is the original configuration of L0 and D0. And after deformation, you can see the green configuration. It's in the plane. So, this part elongated by the amount of delta L. So delta L divided by L0 is called tensile strain. But there's also lateral strain, which is perpendicular, which is equal to the minus D divided by D0. Can somebody tell me why there's a minus sign? All right, this delta L, is it positive or negative?
The delta L?
Yeah, right here. It's positive because it's under tension, so it's elongating, right? But in the lateral direction,
So you can make it through the tree.
it shrinks. It shrinks. So one is plus, another one is a minus. So what is the The shear strain gamma, you can see this was a square before, and it was sheared by the amount of delta x. So then the shear strain gamma is equal to the delta x divided by y, and it's also equal to tan theta, and theta is this angle here. You can see that both tensile and shear strains are dimensional. They don't have dimensions, because here we have length divided by the length. Now this is actually the definition of the tangent function. It's the opposite side to the next side. So delta x over y. That's the definition of this thing. Useful relationships that we're actually deriving in that other class is that delta L is equal to the FL0 over EA0, where L0 is the original length, F is the force, E is the elastic modulus, A0 is the original cross-sectional area. Or delta D is equal to the minus nu FD0 over EA0. Nu is the Poisson's ratio. Poisson's ratio is something that I need to tell you about because of the values. This is how the actual tensile machine looks like. Not in schematic, but the actual thing. So when I said that unloading is always elastic, if this is the stress strain curve, this is stress, this is strain. The stress has dimensions of pascals. Strain has no dimensions. It's meters divided by meters. So then each data point on this curve would have what kind of units? Because the stress is measured in pascals. Pascal. And what about the proportionality constant between the stress and the strain? Where strain has no units. What would be the units of that? Also pascals, because on the y we have pascals, on the x we have no dimensions. So each data point on this curve has the units of pascals, and the slope, this slope. And then when I meant unloading is always elastic, you see this? This is the unloading. But what I wanted to show you is this Poisson's ratio business. Where is that? Oops. Here. The Poisson's effect is this. We put this in tension, so this piece of rubber elongates. But the lateral dimensions change, and it shrinks. So by definition, it's the lateral strain is strain in this direction divided by the strain in this direction. And if I'm applying tension here, this becomes longer, but in this direction it becomes thinner. Is this a plus? Okay, what about this direction? It's a minus. When you look at the table, all the values are positive. The reason they're positive is because in the equation there's a minus sign. So we have minus the lateral strain divided by the longitudinal strain. And for every material, there's a table of this Poisson's ratio. And the maximum value of Poisson's ratio is 0.5. Can somebody intuitively tell me why is it 0.5, the maximum value? We can break it, but once we don't break it, you're on the right track. So what about this and why it cannot be more than 0.5? It's going to be too thin. While it gets thinner in this plane, does it get thinner in this plane as well? Okay, so this is the answer to your question. Because there are two lateral strains. There's a strain that in this direction makes this less wide, and there's another strain in this direction which makes it less thick. You see it, right? It becomes thinner and becomes narrow. So I'm in Poland, and there's this research group on the measure mechanical properties of cells. There's a graduate student that shows the data, and I see pH, number 5, for the Poisson's ratio. And I raise my hand, I say, co to je? What is that? And they say, pan rozumie po polsku. I go, tak nie. No, but I teach mechanics of solids, and I know that the maximum value of Poisson's ratio is 0.5, and they made a mistake, and they used 5 instead of 0.5. Now, there could be some artificial material, which you see over there, and then if you expand it, it's going to expand that way, and that structure has Poisson's ratio of 1. But homogeneous continuous materials has a maximum value of 0.5. This is the reason I'm asking you to remember certain things, not because they have any significance, but so that you would avoid making a mistake. Most of the materials have Poisson's ratio of 1/4, 0.25. Then the next one is 1/3, 0.3. And then polymers have the Poisson's ratio of 0.5. And a very important piece of information for you, which I only learned by doing research, because nobody told me that explicitly when I was taking this class. When the material undergoes plastic deformation, Poisson's ratio reaches the maximum value of 0.5. So even though you take a piece of steel, which has Poisson's ratio is 1/3, when you plastically deform it, it goes to 0.5. And guess what? ChatGPT knows about it. Ask Google, what is the Poisson's ratio of a material that is being deformed plastically? Do it. Fact check me. Okay. Another type is torsion. That's what we're going to do today in the next class. So what did it say? Is there an answer? Google gives you an answer? Ask Google. Ask why. Sometimes the simplest questions are the hardest ones, because you may not know why. That's what it says? And then we just made shit up about the dislocation. I like it. It's a lot. It's a good one. Yes. It was not a lot. It was just two different concepts. Yes.
What does it say about if it was greater than 0.5, then it violates the conservation of mass, but if it is less, then it contradicts this.
When was the last time you washed your floor? When was the last time you did laundry by hand? What do you mean? Shh? Go to another country and try to figure out how the laundry machine works, how to pay for it in local currency. And you're going to resort to washing your clothing by hand. And once you're done washing your clothing by hand, what do you do with it? You just take damp, like clothing that's full of water, that's wet. How do you get rid of water in your clothing? What do what? Yes, and what do you do then? How do you do it? You twist it by opposite direction. You see here, this is a bar, and when you twist it in the opposite directions due to this moment, there's going to be a certain angle of twist alpha. You see this? There's an angle. And that angle of twist is equal to the moment, and L0 is the original length, and D0 is the diameter, and G is the shear modulus. And it's equivalent to the elastic modulus E. So if you see G, that means shear modulus. Elastic deformation. So if we plot stress versus strain, see this? Initially, the deformation is elastic. So stress is proportional to strain. And there's Hooke's law that says that sigma is equal E epsilon, where E is the elastic modulus, epsilon is the strain. And E is called modulus of elasticity, Young's modulus, or elastic modulus. There are three different names, but they mean the same thing. Elastic modulus, modulus of elasticity, Young's modulus. The units for the elastic modulus are the units of pressure because it's the proportionality constant between stress and strain. And during this deformation, we're just stretching the bonds between the atoms. That's what's related to this course. If we look at the comparison of 4 classes of materials, we see that there is no material that has higher elastic modulus than diamond. What is the elastic modulus of diamond? I also want to bring your attention that this is a logarithmic plot, meaning that you see here, this is the power of 10. So this is 10, this is 100, right? Not exactly, but the reason it is nonlinear is because this is a logarithmic scale. So the distance between 1 and 2 is larger than between 2 and 4, and see this gets compressed. And with every power of 10, so this is 1, 10, and 100, this is nonlinear scale. In fact, if you take most of your data and you plot it on the logarithmic scale, it's going to look like a straight line. What is the elastic modulus of diamond? 1,000 GPa. I had a graduate student. He measured elastic modulus of silicon carbide films, 3,000 GPa. I said, tomorrow we're getting a Nobel Prize.
Ooh.
And I didn't get that prize.
Ooh.
Why? Yeah. Why? What was wrong? We were conducting other kinds of experiments where we were trying to glue something in situ in that machine, and super glue evaporated into the transducer and glued it shut. So that's how he measured the stiffness of 3,000 GPa. It was a machine error. And that's why I want you to know that the elastic modulus of diamond is 1,000 GPa. Because we're going to be making calculations, you're going to kind of like have a feeling of 1,000. What about steel? What is the elastic modulus of steel? 200. How do you know? Yeah, what about aluminum? Or what about glass? What? No. You can look, it's behind, right there. You cannot tell. 70 for aluminum. What about glass? How do you know that? We've gone over this. You remember. That's good. But it's counterintuitive because if you take a piece of aluminum and you try to scratch glass, which one is going to scratch? So we can scratch aluminum with glass, correct? And what does the scratching business have anything to do with the elastic modulus? It's not. That's the reason when you go on the beach, you have your glasses, whether they're made of plastic or whether they're made of glass, don't put them in the sand, because the sand is going to scratch your glasses because of small contact area. And hardness and the scratching business, they're all measures of plastic deformation, not elastic deformation. But you can see here and appreciate the difference between elastic modulus of metals, like tungsten is around just 400, and diamond is here around 1,000, and the true solid is typically around 1 gigapascal. So the range is from 1 to 1,000, and it is the stiffness of the material. So during elastic deformation, we have our atoms, and we apply the force and we get this delta L. This delta L, or elongation of the sample, consists of the stretching of the bonds between the atoms, but the atoms do not move from their positions. They remain where they are. And do you remember that well where you were calculating the force in this class? Do you remember that? Force and the energy? That slope determines what the properties, elastic properties, are going to be. There are linear elastic materials where the stress is proportional to strain. But some materials are non-linear elastic, like this rubber. And I'm not going to get into the details, but you can see that this rubber comes back to its original length. Its length does not change. For most of the design problems, you don't want to have any permanent deformation. So it's reversible. Or like this. And that's what it comes down to, is interatomic bonding and the force between the atoms, because this modulus is proportional to the slope of the interatomic force interatomic separation curve, and this is the distance, df dr. I already discussed the Poisson's ratio, but this is another way of looking at it. If we plot epsilon x, and x is this direction, versus epsilon z, where z is perpendicular, we can see that we go from tension to compression. And the slope of that is minus the Poisson's ratio. And it is like this because when the strain in the x direction is positive, the strain in the z direction is negative. You see that? That's why this curve is going to be like this. And for most of the metals, it's 0.3. And for ceramics, it's 0.25. And for polymers, it's 0.4. It goes up to 0.5. But it's a fraction. And for all of the materials, it varies between 0.15 to 0.5. And I want you to remember this range. It's not so hard to remember. There are other elastic properties, like shear modulus. When you take a material and you try to twist it, it also resists. Like imagine taking a paper clip, and if you plot the shear stress versus shear strain, then the proportionality constant is called shear modulus G. That little fish on the bottom of the sea is under hydrostatic compression, and there's bulk modulus, that if we take the change in the volume of minus delta V over V0, then K is the bulk modulus. And there's a relationship between, for isotropic materials, between the shear modulus and the elastic modulus. So shear modulus is equal to E divided by 2, 1 plus nu. And you can see that depending on what the Poisson's ratio is, the shear modulus is roughly half of the elastic modulus. And the table typically would list both shear and elastic modulus, and this is a relationship for the bulk modulus. Okay, plastic deformation for metals. During loading, we can bypass the elastic limit. And the elastic limit is measure of plastic deformation. So metal continues to deform under more or less constant value of stress. If it is elastic perfectly plastic, then this is going to be a horizontal line. And during this process, we have both contributions to the elongation, elastic and plastic. And that's when the dislocations physically move in the material. Now, upon unloading, the plastic deformation is not recovered. Only elastic deformation is recovered. So I don't have a paper clip, but I do have this piece of paper I'm going to demonstrate again. I bent it 90 degrees, and then I let go, and it doesn't spring back to all the way. And this amount of deformation is recovered, and that is not. So plastic deformation stays there. Those planes physically moved, and they stay there. But because the atomic bonds are stretched, they're still relaxed once we get rid of the load. The whole mechanics course crammed in a couple of lectures. So that's why you don't see the derivation, you just see the final result. So plastic deformation, synonym is permanent deformation. And for design, we're always trying to avoid it. It's non-recoverable. That's why after a fender bender, you have to take your car to a mechanic or to a body shop for them to restore the shape of the metal. Majority of the designs are going to be here in the elastic region. Otherwise, the part changes its dimensions and it doesn't fit anymore. So, we have elastic deformation by stretching the bonds here. We can unload and we're going to go back to zero stress and zero strain. Here we have elastic and plastic deformation, motion of dislocations. Upon unloading, the original loading slope is repeated so that these two straight lines are parallel like this. And then this is the amount of epsilon sub p, or plastic strain, which is not recovered. This allows us to measure another very important property for a metal, which is called yield strength. And yield strength is determined by what is called 0.2% offset. 0.2% is easy to remember. And you can always convert 0.2% into the fraction. How do you convert percentages into fraction? Divide by 100. So 100% is 1, 50% is 0.5, a quarter is 25%, okay? So please remember, 0.2%, 0.2%, repeat, 0.2%, 0.2%. I'm going to explain what that 0.2% means. We get our data. This is the data of the stress strain curve on the tensile machine. We go in here to 0.2%, which is 0.002. And then we repeat the slope like that. And where that slope intersects our data, that is the yield strength. And we go in here and we say, that's the value of the yield strength. So the yield point, or yield stress, or yield strength, meaning the same thing, is a data point on the stress strain curve. And it has the units of pressure, pascals. And also the elastic modulus, which is this slope, has the units of pressure, pascals, because this is in pascals and this has no units. Two parameters, two properties for a metal: elastic modulus and yield strength. You can see here that there is no data for ceramics. And when we're going to get to ceramics, we're going to discuss why. But imagine you're taking a piece of metal and you are stretching it. Is it going to stretch? Yes, maybe. You take a paper clip and you bend it. Is it going to bend? Yes? And then imagine you take a piece of glass and you bend it. How far is it going to bend? You see? This is the fundamental difference between classes of materials, of how they respond to load. Metals, ceramics, and polymers. To control the process, to control the structure, to control the properties. And now we're discussing properties. And we'll continue next week.